Now we will come to the next point, superconductors. Now these superconductors actually in a normal condition, all the conductors they offer resistance when the electric current flows through them. Okay, either the resistance can be less or it can be more. All the conductor they offer resistance, and the part of electrical energy, okay, and the part of electrical energy is wasted in the form of heat energy. So this happens in almost all the conductors. But it was found, one scientist was there, that is a Dutch physicist, that is 1811. He took a metal called mercury. Okay, he took the conductor mercury, and he reduced the temperature up to 4.2 Kelvin and minus 269 degrees Celsius. That means he reduced the temperature of that metal, and it was found that the metal, when the temperature of that metal, the mercury, is reduced, okay, the resistance becomes zero. There was no any resistance offered by the metals. So, and he gave that metal as superconductors. Okay, and there are the various metals apart from the mercury. There are the other metals are also there. That is tungsten is there, lead is there, mercury. All these are considered as a superconductor because their resistance will become zero. No resistance. Almost all the conductor will offer resistance, but these are the metals like the lead, mercury, and the tungsten, which do not offer any resistance. And the resistance will become zero when the temperature is abruptly they reduce to 4.2 Kelvin or minus 269 degrees Celsius. When the temperature is reduced drastically to this temperature, okay, the resistance will become zero, and when there is no resistance offered by the metals, they are considered as the superconductors. So therefore, we can say that a superconductor means it is the property by virtue of which a conductor shows almost zero resistance at a very low temperature. So superconductor are the conductor which shows zero resistance at a very low temperature. So this is known as the superconductor. Next one. And the application of the superconductor. So that means if there is no if there is no resistance offered by the superconductor, which means that there is no loss of power, no power loss. So now this superconductor has got uses. Okay, they have got a very important use in the field of technology. Okay, number one use is that they are used to produce a very high speed and very small sized computer. Okay, so these are used in a very high speed and a small size computer. So you can see the computer also, when if there is electric failure also, it keeps on working. Okay, because there is no resistance offered by the superconductor. Okay, and even if the power failure, they works, they functions. Okay, so these are used in to produce a high speed and a small size computer. Okay, and the other one is there. These are also used to produce electrical power transmission for a long distance. Electrical power transmission for a long distance because there is no any loss of power since there is no resistance. So there are the two uses, applications of superconductor. Now let us come to the next point, that is specific resistance and resistivity. Okay, specific resistance and resistivity. So now we know that, now considering the factors affecting the resistance of a conductor. So resistance of a conductor is directly proportional to length, and resistance of a conductor is inversely proportional to area. So combining these two equations, what I can do, I can take common here. Resistance is proportional to length into 1 by area. So resistance is proportional to L into 1 will be L divided by A, then R equals to, now this sign of proportionality I write here P L A. Okay, now this P is constant, and this constant is known as the resistivity or the specific resistance, and this is written as rho, RXO rho. Okay, so R equals to PL divided by A, or what I can do, I can cross multiply here. PL equals to RA, or P equals to RA divided by L. Understood? So this is specific resistance or resistivity. By taking the factors of resistance, which is directly proportional to the length, inversely proportional to the cross-section area of the conductor. So combining the two equations here, so R is proportional to L by A, R equals to, this sign of proportionality is replaced by P, so this P is resistivity or specific resistance, which is written, which is read as rho. It is not read as P, but it is read as rho. So cross multiply here, PL equals to RA, P equals to RA divided by L. So this is specific resistance. So therefore, now we come to the point specific resistance. Now what is specific resistance? Means specific resistance of a material is the resistance offered. Okay, it is the resistance offered by. Now specific resistance or resistivity is the resistance offered by 1 meter length, wire having a cross-section area of 1 meter square. Okay, so from here we can find the definition of specific resistance or resistivity, which means that specific resistance or resistivity is the resistance offered by a wire of length 1 meter having a cross-sectional area of 1 meter square. Okay, so from here you can find the SI unit of resistivity. So how will you find the SI units? So look at it. P equals to, that is rho equals to, SI unit of resistance is ohm. I'll write it here ohm. SI unit of area is meter square. Then again SI unit of length is meter. This square and this meter will cancel this. Therefore rho equals to ohm meter. Or I can write it here ohm meter. So the SI unit of resistivity is ohm meter. So how we are getting is by replacing the value of resistance and the length and area. So SI unit of resistance is ohm, SI unit of area is meter square, SI unit of length is meter. So 1 meter and the other meter at the denominator cancels. So what will remain? Ohm meter will remain. Therefore the SI unit of resistivity is ohm meter, or symbolically it is written as ohm meter. Okay, so this is the unit of resistivity. Okay, the next point is here the resistivity of silver. Okay, so resistivity means, what is the resistivity is? It is the resistivity or the specific resistance is the resistance offered by 1 meter length wire having a cross-sectional area of 1 meter square. So sometimes it may come the resistivity of silver, which is given here 1.6 into 10 to the power of minus 8 ohm meter. What does it mean? Explain the statement. This may come here. Okay, so you have to explain this. What does it mean? Is that it means that if we take a silver wire, resistivity of silver is 1.6 into 10 to the power minus 8 ohm meter, which means that if we take a silver wire of length 1 meter, okay, cross-sectional area 1 meter square, then the resistivity of the silver will become 1.6 into 10 to the power minus 8 ohm meter. Okay, so what does it mean? Is that if you take a silver wire of length 1 meter having a cross-sectional area 1 meter square, then the resistivity of the silver will be 1.6 into 10 to the power minus 8 ohm meter. So this is the explanation of the term 1.6. The resistivity of silver is 1.6 into 10 to the power minus 8 ohm meter. Okay, so this is this is about the explanation of that. Now next point, let us come to the factors affecting the resistivity. Now what are the factors that affects resistivity? There are the two factors. One is the nature of the material. Okay, nature of the material. Nature of the material means what the material is made up of. Okay, either it is made of silver, it is made up of lead, it is made of aluminium, copper. That means nature of the material. Other one is the temperature of the material. So resistivity depends upon the two factors. One is the nature of the material, other one is the temperature of the material. So this is about the electric current. Okay, current electricity. So in the next class I'll discuss about the cell, about the EMF of the cell, terminal voltage drop, parallel combinations of a circuit and the series combination of the circuit. Thank you.